Welcome to AskPrep, your trusted companion for NEET and JEE preparation. Today we will study about a very important topic of chemistry, which is GOC, General Organic Chemistry, Advanced, Hyperconjugation and Inductive Effect. General Organic Chemistry, or GOC, is a fundamental concept in organic chemistry that helps us understand how organic molecules behave under different conditions. It provides insight into the electronic effects that influence the stability, reactivity, and properties of various compounds. Among these effects, hyperconjugation and the inductive effect play a crucial role in determining the stability of carbocations, reaction mechanisms, and the overall behavior of organic molecules. Hyperconjugation is a phenomenon where the delocalization of electrons occurs due to the interaction between sigma bonds, particularly CH bonds, and an adjacent empty or partially filled p orbital or pi system. This effect is often referred to as no-bond resonance because it involves the delocalization of electrons without the actual formation of a new bond. One of the most significant applications of hyperconjugation is in the stability of carbocations. The greater the number of alkyl groups attached to the positively charged carbon, the more hyperconjugation takes place, leading to increased stability. This is why tertiary carbocations are more stable than secondary or primary ones. The concept of hyperconjugation is also observed in alkenes. In substituted alkenes, hyperconjugation helps in the distribution of electron density, thereby influencing the stability of different isomers. More substituted alkenes tend to be more stable due to the hyperconjugative effect, which is a key factor in determining reaction pathways in organic synthesis. This effect also explains the reason behind the preferred orientation of certain reactions, such as electrophilic addition reactions in alkenes. Another important electronic effect in organic chemistry is the inductive effect. The inductive effect is the shifting of electron density along a sigma bond due to the electronegativity of atoms or groups attached to a carbon chain. It can be classified as either a plus I effect or AI effect, depending on whether the group donates or withdraws electron density. Electronegative elements, such as fluorine, chlorine, and oxygen, pull electron density away from the carbon chain, exhibiting a negative inductive effect. On the other hand, alkyl groups donate electron density through the sigma bond, exhibiting a positive inductive effect. The inductive effect significantly impacts the acidity and basicity of organic compounds. For example, when an electronegative atom or group is attached to a molecule, it withdraws electron density and stabilizes the negative charge on a conjugate base, thereby increasing the acidity of the molecule. Conversely, electron-donating groups decrease acidity and increase basicity. This principle is crucial in understanding the behavior of carboxylic acids, amines, and other functional groups in organic chemistry. The inductive effect also plays a role in determining the stability of charged species in reactions. In carbocations, electron-donating alkyl groups stabilize the positive charge by releasing electron density. This explains why tertiary carbocations are more stable than secondary or primary ones. In contrast, electron-withdrawing groups destabilize carbocations but stabilize carbanions by reducing the negative charge concentration. Hyperconjugation and the inductive effect often work together to influence the outcome of chemical reactions. In electrophilic aromatic substitution reactions, for instance, the positioning of substituents on a benzene ring is determined by these effects. Electron-donating groups activate the ring towards electrophilic attack, while electron-withdrawing groups deactivate it. This knowledge is essential in designing synthetic pathways and predicting reaction outcomes in advanced organic chemistry. Understanding hyperconjugation and the inductive effect is not only important for theoretical knowledge but also has practical applications in pharmaceuticals, materials science, and industrial chemistry. These effects influence the design of drug molecules, optimizing their stability and reactivity to enhance therapeutic effectiveness. In polymer chemistry, the stability of certain monomers and intermediates is dictated by these electronic effects, impacting the properties of the final material. Hyperconjugation is not limited to carbocations. In alkenes, it helps in stabilizing the double bond. The delocalization of sigma electrons into the pi system reduces the bond strength disparity between the double and single bonds, imparting extra stability to the alkene. This explains why more substituted alkenes are more stable than their less substituted counterparts. Hyperconjugation also plays a role in explaining bond length variations. Single bonds adjacent to double bonds tend to be shorter than expected due to partial double bond character introduced by hyperconjugation. The inductive effect, on the other hand, involves the transmission of electron density through sigma bonds due to the electronegativity differences between atoms. When a highly electronegative atom or a group is attached to a carbon chain, it withdraws electron density, creating a dipole. This withdrawal is referred to as the negative inductive effect, or I effect. Groups such as halogens, nitro, and carbonyl groups exhibit this behavior, making the attached carbon more electron deficient. This influences the reactivity of the molecule, particularly in reactions involving nucleophiles and electrophiles. With advancements in research, the study of these electronic effects continues to evolve. Computational chemistry and spectroscopy techniques provide deeper insights into molecular structures and reaction mechanisms. Scientists use these principles to develop new catalysts, improve reaction efficiency, and create more sustainable chemical processes. The interplay of hyperconjugation and inductive effects extends beyond textbook chemistry and finds relevance in innovations across multiple scientific disciplines. Thank you. We hope this video has helped you gain a clearer understanding of hydrogen and its compounds, especially the fascinating role of heavy water and isotopes. If you found this video helpful, make sure to like, share, and subscribe to AskPrep for more in-depth chemistry lessons. Keep studying, stay curious, and good luck with your exams.